Did you know that some problems in math are not just difficult, but literally impossible to solve? Not because they're too complex, not because we haven't found the right approach, but because they are fundamentally unsolvable. For centuries, mathematicians believed that every problem had an answer. But then, one discovery shattered that belief forever. A discovery that linked two seemingly unrelated problems into one terrifying conclusion. This is the story of Hilbert's 10th problem and the halting problem, and how their connection proved that some doors in mathematics will remain locked forever. In 1900, the world's leading mathematicians gathered in Paris for the International Congress of Mathematicians. At that event, one man stood before them with a vision of the future. David Hilbert believed that mathematics was the ultimate tool for understanding the universe. He saw it as a perfect logical system where every question had an answer waiting to be found. And to push math forward, he proposed a challenge, a list of 23 unsolved problems that mathematicians would need to solve to complete the mathematical puzzle of reality. Most of these problems were eventually cracked, but one of them, problem number 10, would prove to be different. It would remain unsolved not just for years, but forever. At first glance, Hilbert's 10th problem seemed simple. Can we create an algorithm that determines whether a mathematical equation has whole number solutions? For example, given an equation like this, is there a whole number solution for x and y, yes or no? Hilbert wanted a single algorithm, a universal method, that could take any equation and instantly determine whether it had solutions in whole numbers. It seemed like a reasonable request. After all, mathematicians had already found algorithms to solve many types of equations. Why should this be any different? But it was, and proving that would take nearly 70 years. Mathematicians initially believed that either 1, a universal algorithm existed but was just very difficult to find. 2, the problem was too vast, but could be solved in smaller specific cases. Or 3, there was no algorithm at all, meaning some mathematical questions would remain forever unanswered. At first, option number 1 seemed the most likely. Throughout the early 20th century, mathematicians attempted to find a universal method. They tried everything algebraic techniques to break equations down into simpler forms. Number theory to detect patterns in whole number solutions. Early computational approaches to systematically test equations. But each attempt ran into the same problem. Some equations were simply too unpredictable. No single formula could account for all of them. Still, many mathematicians believed the right algorithm must exist, it just hadn't been found yet. When no universal method appeared, some researchers suggested that maybe the problem wasn't impossible, just too difficult to generalize. They tried to categorize different types of equations and solve them case by case. This worked for some, but others remained stubbornly resistant. As mathematicians worked, they started seeing something troubling. Certain equations seemed to behave unpredictably, almost chaotically, with no pattern at all. And that's when the problem took an unexpected turn, into the world of computers and logic itself. In the 1930s, a young mathematician named Alan Turing was tackling a completely different problem: the limits of computation. Turing wondered, is there a way to create a perfect machine, a computer, that could solve any mathematical problem by following a set of rules? To test this idea, he imagined a machine that could read instructions from a tape and execute commands, a model we now call the Turing machine, the foundation of modern computers. But then Turing stumbled upon a disturbing realization. Turing's question was this: given any program and an input, is there an algorithm that can determine whether the program will eventually stop, or halt, or run forever? For example, Imagine a program that loops infinitely unless a specific condition is met. Can we create a separate program that always predicts whether the original program will halt? Turing's answer was shocking. No, we cannot. He proved that there is no general algorithm that can determine whether any arbitrary program will halt. Some computations will forever remain unpredictable. And this had massive implications, not just for computers but for mathematics itself. For decades, Hilbert's 10th problem and the halting problem seemed unrelated. One was about numbers, the other about computation. But then in 1970, a breakthrough came from an unexpected place. A young Russian mathematician named Yuri Matyasevich. Matyasevich realized something incredible. Hilbert's 10th problem was just another version of the halting problem. He showed that certain equations in Hilbert's 10th problem behaved exactly like computer programs. Some equations halted, meaning they had whole number solutions, while others ran forever, meaning no solution existed. But since the halting problem had already been proven unsolvable, this meant that Hilbert's 10th problem was also unsolvable. This was the final nail in the coffin. Hilbert's dream of a complete solvable mathematics was shattered. Hilbert's 10th problem wasn't just about equations. It proved that mathematics itself has limits. Some problems will never have answers. This realization changed everything. It meant that even with unlimited time, unlimited computing power, and unlimited mathematical knowledge, certain questions in math will remain forever out of reach. So next time you hear someone say that math is the key to understanding everything, remind them, some doors in math will always remain locked. If you love uncovering the strangest, most mind-blowing facts, don't forget to like, subscribe, and hit the bell icon so you never miss an episode. Thanks for watching, and I'll see you next time.